Mark Huckvale has been Senior Lecturer in Speech Sciences, Phonetics and Linguistics at the Department of Speech, Hearing and Phonetic Sciences at University College London since 1990. And previous to that, he studied at the University of Warwick and the University of London. His expertise within the field of speech science and phonetics touches many areas. His publications include works in areas of speech recognition and speech synthesis, speech intelligibility, spoken language acquisition by machines, as well as several aspects of metrics and modelling of speech. His current research, moreover, includes work with Ian Howard, also at UCL, in a project entitled Teaching an Articulatory Synthesizer to Imitate Speech. I hope that list does justice to the breadth of your work, Mark. He's developed software for speech analysis that continues to be important to many generations of students and researchers. Names such as WASP and SFS are now well known and have been joined by other recent applications such as Furison and RT Pitch and E-section, which Michael showed us in his talk yesterday. There's no doubt that Mark has a wealth of experience in just the sorts of visualization areas that this conference is exploring. He's also extremely generous in sharing and communicating his expertise, as you can see from his UCL website, where his web pages offer teaching resources such as web tutorials of many kinds for speech science students, as well as advice on such down-to-earth matters such as choosing speech recording equipment and even how to construct your own valve resonator in a workshop from plastic tubing. We're delighted that he's accepted our invitation to speak here at AVML, and he'll be presenting his keynote, which is entitled Speech as Visible Patterns of Sound. Thank you very much, Mark.
Well, introduction. Thank you very much. Okay, so as Anna said, I've done a lot of work over the years in writing software tools for speech analysis, for speech synthesis, for speech processing, for speech modeling. And what I'm really doing today is going to give you a kind of a sort of scattershot of approach of a whole load of these different things. I'm going to demonstrate a lot of these tools to you today. I've chosen tools, it's a subset of the stuff that I've done, but I've chosen tools on the basis as do these tools provide us some kind of a visual analysis of speech which gives us a greater understanding of the nature of speech. And the tools cover quite a range from, you'll see, from most basic kind of oscilloscope sort of display up to stuff looking at accents and speech recognition and looking at dialogue. Many of these students were written with students in mind, and as Anne said, I produced a lot of this software to help students in the laboratory, allow them to learn about speech and to do their own project work. But I'll also, in this presentation, I'll also show you some bits of visualization which are related to my own research as well, and to clinical applications. And lastly, one of the things I had in mind while I was preparing what I was going to show you, I had in mind the advice of Edward Tufte, which is about the kinds of things that the graphics displays should do. They should show the data, they should tell the truth, they should help the viewer think about the information, encourage comparison, and trying to make large data sets coherent. So hopefully in the background, as we go through this, I'll maybe be able to pick up a few aspects of this and think about the choice of visualization and how that helps the viewer and helps you to interpret the data. Okay, so we're going to start with some really sort of basic stuff, and I apologize if this is too basic. So I'm going to put my microphone on, and we'll look at some speech sounds. So the first place to look at speech sounds is to say, well, what's the signal coming from the microphone? So let's have a look at the signals coming from the microphone. And so this application, let's get rid of this bottom half of this picture. So now when I'm speaking, I'm changing the sound pressure in this room, and through my movement of my larynx, making local sound pressure variations here, and those sound pressure variations are going out into the room. And this display is simply showing us essentially the pressure in the room at any particular time. If I'm quiet, then that line there really represents atmospheric pressure. And if I go ah and freeze the display, then I've got making these fluctuations in atmospheric pressure. And a good question I always ask the students is, how big do you think these fluctuations are? I mean, how big are these fluctuations compared to atmospheric pressure? And of course, if you're with this at all, you know that they're really, really, really small. These pressure fluctuations are probably about 1/10 of a Pascal. Maybe that doesn't mean anything because you don't know what atmospheric pressure is, but atmospheric pressure is 100,000 Pascals. So these are about 1/1,000,000th of atmospheric pressure, these fluctuations. And these fluctuations that I've produced here are 1,000 times bigger than the quietest ones that you can hear under optimal circumstances. So the quietest sounds that you can hear under optimal circumstances are 1,000,000,000 times a fraction of atmospheric pressure. And that's what it's really saying is that our mechanism, the fact that we can hear sounds at all, is because we have this fantastically sensitive mechanism for picking up these pressure fluctuations, which is our organ of hearing. And the other thing you can see from these kinds of pictures is that the fluctuations are also quite rapid. This display has only got 40, 50 milliseconds, or 20th of a second across the display. And so the fluctuations are actually hundreds of times per second or thousands of times per second. So we're talking about very rapid fluctuations, much faster than you can see if they were visible, and also extremely small. And so that's emphasizing again the power of our auditory system. Now, the sound propagates from me to you, and in doing that, it has to go through the air. And here's a nice simulation of the movement of sound through air. And this simulation was brought to my attention by the head of my head of department. And he said, "Isn't this a lovely simulation? This is showing you how sound is traveling through air. Here's some sort of a diaphragm of a loudspeaker, and it's compressing the air, and that compression wave is moving through the air. But in fact, each individual particle is just oscillating. Like this, maybe you can see this little orange square. Each individual particle is just oscillating around one position. And of course, it really addresses a problem that students always have, is that they don't understand the difference between air movement, the transport of air, and the transport of sound. Transport of air, and one of the reasons they get confused in speech, of course, is that in making a vowel sound, we push air out. And so it's not surprising that they have to have air movement to make a vowel, so then they confuse air movement with the sound itself, whereas, of course, you can make sound and you can make vowels without any air movement at all, as long as you've got a sound source somewhere at this end of the vocal tract. It turns out that this is probably the only one of the demonstrations I'm giving you today that I didn't program myself. And there's an interesting story related to this, which is that I tried to do this many years ago, to build a simulation of sound going through air, but I took completely the wrong approach. I did a simulation, a two-dimensional simulation of a gas. I did a physics simulation of a gas, in which particles bounced around and hit each other, and by that process, energy was transformed and transmitted through the gas. If you look at this simulation, it's completely fake, because the dots don't interact with one another. They don't touch one another. They don't bounce off one another. These are not air particles. These are little atoms of bits of dust floating in the air, and what we see is the movement of the dust particles. We don't see the movement of the air molecules itself. And so this is a situation where, if I told you the truth, if I actually did a gas simulation, it doesn't work. You can't make this happen. And the reason you can't make it happen is that the number of particles that you can simulate in a real physical simulation is about equivalent to a hard vacuum. And so that you don't get sound transmission through gases with numbers of particles that you can actually simulate on the computer. So you have to fake it to get this beautiful simulation. And you can still tell students that, oh, this, sound is not air movement, and that sound particles don't change position when the sound passes through them. But at the same time, you're lying to them, because this simulation doesn't actually demonstrate anything of the sort. It's just simply an animation, which is a long way from the truth. Okay, so sound is traveling out there and being picked up by your auditory system, and we have these different perceptual dimensions of sound. One dimension is loudness, how big the sound pressure waves are, and the second perceptual dimension of sound is pitch. And it's interesting that people have a lot of problem with pitch. They find it hard to judge, is the pitch of the sound going up or is it going down? And just judging the height of pitch, just judging how the pitch is changing, people find difficult. So this is clearly a really good opportunity for a visualization of pitch. So let's try and run this. So 1, 2, 3, 4, 5. Okay, so this is a display where it's actually analysing the pitch of my voice as I'm speaking, and that the graph along the bottom really represents the pitch contour. It's overloading slightly the microphone. And so as I'm changing the pitch of my voice, this line there in the bottom display is changing in height. So horizontal dimension is time, vertical dimension is fundamental frequency or repetition frequency of my voice. There was once a young rat named Arthur who could never take the trouble to make up his mind. And as I'm speaking, the pitch of my voice is changing, and that aspect of speech, that intonational aspect of speech, is something that you can then see. You can see the change, you can see the rising and the falling, and you can, of course, experiment with things yourself. And of course, this sort of application has people find a lot of useful in things like teaching of English as a foreign language as well, to try and explain to people what different pitch accents are and how they're used functionally in language. Another thing you can use this for is to demonstrate that loudness and pitch is not the whole story, because I can go think and do this. So that my voice is tremoring, but the changes in quality of the sound is not the same as changes in pitch. So we could say change the pitch of sounds independently from the timbre or the quality of sounds. So it says that basically there must be a mechanism within our hearing organ which gives us something other than loudness and pitch, which is this quality or the colour, or we say the timbre of the sound. So this gives us another opportunity for a different simulation, a picture which tells us more about timbre. So we can go back into to our waveform picture, and we can ask what are the elementary frequency components in this sound, and take this sound, break it up into its elementary components in a kind of analogous way to the way in which the ear takes a sound and breaks it up into its elementary sound components. And the way we do that conventionally in digital signal processing is through a Fourier transform. So we can so I can make a sound, and then this graph at the bottom really represents the frequency components of the sound, the spectrum of the sound, sort of like the fingerprint of the sound, and these fine sort of teeth of the cone here are the elements that are called harmonics. And the overall shape of this thing here is the characteristic which gives us that perceived quality of an R vowel. We try a different vowel, R, E, then the different quality vowel has a different fingerprint. It has a different shape. And sh, it's a characteristic for sh, and s, characteristic for s is different again. So all of these differences we think of as timbre rather than pitch can be explained by the shape of this fingerprint, the shape of the frequency components that are present in the sound. So then we say, okay, so we try to say that the frequency components are important for timbre, but then we've actually made an enormous jump, because we've sort of said that these frequency the science has said these frequency components are important, but we haven't really explained how the ear is able to extract what these frequency components are. Actually, sorry, I'm getting ahead of myself. Oh, so we're going to come back in a minute then to look at how the ear generates processes of timbre. But before we do that, let's just talk about looking how this spectral representation not only varies across different vowels, but varies across time. So that if we can say that this fingerprint is different for different vowels. R has one shape, e, oo, they all have different shapes, but we don't speak, we don't communicate with one another simply by going up to people and saying ah, and they're going e back to us. We don't not communicating through constant sounds. We're constantly changing and moving our articulators. And so this kind of picture is actually kind of more like a snapshot. It's like going up to somebody and taking a photograph of their speech. So it's what they're doing at one particular time. Whereas clearly, if you're really going to study speech, you need a movie. You need to look at how speech is dynamically changing with time. And of course, when you start to look at speech in a dynamic sense, you find that it's becomes actually quite complicated, and also it also changes extremely quickly. So Michael showed some video pictures yesterday. Here's another video, a couple of sentences, X-ray video.
Why did Ken set the soggy net on top of his deck? I have put blood on her 2 clean yellow shoes.
And what you notice, of course, is that you get this incredible dance and movement of the articulators, and you get a really powerful visual sense that speaking is not a kind of piecewise stationary process. It's not making a sound and then instantaneously changing to another sound and switching to another sound. As soon as you see articulation like that, you realize that you've got asynchronous movement of the articulators, and the articulators are always moving. There's no point when the articulators are stationary. And you can see that same story, of course, when you start to visualize speech sounds as changing with time. Then, of course, you're going to get the same kind of effect. And it's an important aspect of the visualization of sound changing with time is this dynamics, this continuous change, and the continuous value of everything. So to move a snapshot like a spectrum into a movie, we build a spectrogram. We look at how the spectrum changes with time. And in a spectrogram, we're sort of taking a spectrum, and every sort of thousandth of a second, hopefully this is going to be working, so every thousandth of a second or so, you're taking a snapshot of the characteristic of the speech, and you're plotting this on a graph. So on a spectrogram, so we've got time along the horizontal axis, frequency is now going up the page, and the energy at any particular time and any particular frequency is expressed as a level of black. So ah, e, oo, and so different sounds have a different distribution of energy up the page now. So on the spectrum, it was across the frequency axis, across the page, but in the spectrogram, we're now looking at this frequency distribution sort of up the page, and the amplitude axis has been turned into levels of black. Of course, it kind of interesting about why we plot spectrograms this way, of course, and hinted from Michael from last night was, of course, the way spectrograms were made originally was by taking the energy and amplifying it and using it to burn a piece of paper, so that the more energy there was, the greater the burn, and the darker the mark was on the piece of paper. And so this choice of visualization, where the more energy is a darker color and less energy is a lighter color, is actually a kind of historical accident. There's no particular reason it should be done this way. And of course, many people have tried to try and use different kinds of coloring schemes for these sorts of graphs. I must admit, I'm still fairly old-fashioned, and I like to see my spectrograms this way around. And I guess what ultimately matters is what you're comfortable with, and what helps you interpret the pattern. So this spectrogram is dynamics real-time spectrogram. As it's reading in the microphone signal, it's transforming the signal into a frequency representation during Fourier transform. It's then mapping that Fourier transform into a grayscale and putting it on a scrolling display. Again, the interesting thing was, when we first was programming these kinds of things, the computers we had were, of course, much less powerful, and it still amazes me what you can do in real time. I mean, this is doing Fourier transforms of 1,000 points or something, it's doing it many thousands of times per second. So it's doing hundreds, tens of millions, hundreds of millions of calculations per second. And this is just like on a laptop. It's really quite extraordinary what computing power we now have available to us. And this was completely, when I came to University College in 1990, there was nothing. There was nothing like this. There was no real-time displays of spectrograms. And these things really have only been possible in the past 10 years or so, when computers have been powerful enough to do the processing. Okay, so I said I was going to revisit the issue of hearing, and so we see this kind of representation, and we say this is what speech looks like, and with characteristics, this is why one speech sound is different from another speech sound. But it always seemed to me that we kind of fake this, because this isn't the sorts of processing that goes on inside the ear, and the ear doesn't have this computational power to do tens of millions of fast Fourier transforms. So it does the processing in a completely different way. And if we're going to be honest about it, we have to go and address the issue about how real hearing works and how real hearing produces these analyses. And of course that might itself lead to new insights into the ways in which sounds are different to one another, and why speech sounds have been developed and are used in particular ways. So if we only look at the spectrogram, then we're sort of only looking at a kind of an idealized representation, a representation that's idealized for the computer, and not a representation which is really appropriate for finding out how the auditory system looks at speech, or how speech looks to the auditory system. So over the years, again, I've tried to do simulations of hearing to try and explain to students what's going on inside the ear. And I'm going to show you the latest one, and it's probably going to take me about an hour to explain to you how it works and what you can see in it. Unfortunately, in my course, I would have 2 one-hour lectures and a 2-hour lab class on this. So this is it's fantastically complicated, and in a way, as you'll see in a minute, I think that's actually to its disadvantage. So this is a representation of the auditory system processing a sine wave. So this is a sine wave at 500 hertz, and the graph along the top there is kind of meant to represent the auditory signal coming into the ear, the stimulus, the pressure signals coming into the ear, and that goes through the middle ear, moves the tympanic membrane and the ossicular chain, and ends up in the entrance to the cochlea, something that's called the oval window. So this is the boundary between the mechanical movements of the bone chain and the fluid movement inside the cochlea. And this funny shape here represents the basilar membrane, which is the structure inside the cochlea, which essentially decomposes sounds into its elementary components. And you can see this particular sound is causing this particular part of the basilar membrane to vibrate most. And if I increase the frequency, then hopefully what you'll see is it's now this part of the basilar membrane which is vibrating most. So what happens is that each point on the basilar membrane prefers to vibrate at a different frequency. So if you put in a signal which only has one frequency, then only be one place on the basilar membrane that vibrates. So we've got a vibrating basilar membrane, but then of course you've got, sitting on top of the basilar membrane, you've got the organ of Corti, which is the organ which detects the vibration and turns it into nerve firing. And this funny spectrographic picture across the middle of the display is meant to represent the firing, or at least the probability of firing of the fibers in the organ of Corti sitting on the basilar membrane. And you get this very bizarre pattern in which doesn't seem to be the way in which you expect it to be. You get this kind of little zigzaggy pattern. And really what's happening is that this sound wave, you can kind of imagine it traveling down here, and it reaches this part of the basilar membrane, and this bit starts to vibrate and starts to fire, and then it travels on a bit further, and then it reaches this bit, and this bit fires, and then it travels on a bit further, and then this other bit fires. So what you're seeing here is actually this slanty line is really representing the speed with which the energy is moving along the basilar membrane. Even that's a lie, but it's actually called the group delay. But nevertheless, you get a sense that you get this idea of what's called the travelling wave. Well, again, the travelling wave is just an artifact of the way in which the system is filtering. But you get this essentially this movement along the basilar membrane. As I say, I mean, and then finally over here we've got sort of what we call an excitation pattern. It's the sum of all of the nerve firing across frequencies. So I'm just going to stick in something really complicated and we'll move on. Take the frequency right down. So this is meant to represent something like an R vowel. So that waveform shape on there is sort of a simplified version of an R vowel. And what's happening there, because an R vowel now has frequency components at many different frequencies, and so you get a number of different parts of the basilar membrane vibrating at the same time. What you can see in the overall excitation pattern are these bottom ends. You can see these little bumps here, they represent harmonics, and then you can see larger shapes here, and these represent collections of harmonics which are round about particular forming frequencies. So it's looking at this excitation pattern that allows us to identify the resonances, the significant areas in the spectrum which are caused by resonances in the vocal tract, which are caused by particular articulations, which are instantiations of particular vowels. The other nice thing about this kind of picture is that you can see repetition in this picture. You can see places where you see it. So you can see a pattern, and then a little bit later you see the same pattern occurring again. So there's this wiggly line here, and then a little bit later you see exactly the same wiggly line occurring. And so everywhere you look in this pattern, you get a sense that there is something happens, and a little bit later exactly the same thing happens again. And the ear has a mechanism for detecting this repetition and the interval in its repetition, and that's one of the bases of our perception of pitch. Pitch comes from the fact that the ear has a mechanism for looking at intervals, repetition intervals within the neural pattern. And you can explain how, for example, how our sense of pitch works, why it has some of the properties that it has in the simulation. Well, that's enough. This goes on and on and on. And I want to make this important point. This is version 2 of the simulation. Version 1 of the simulation I did of this was basically nothing more than an animation, and it had little triangles that sort of you moved around with the mouse cursor. It didn't really do any filtering. It didn't have any signal processing in it. It was just a kind of a graphical picture of the cochlea and had sort of the coloured shapes that you moved around. And I think actually the students liked the cheaper one and simpler one more than they liked this one. This one actually, it's pretty bewildering what's going on here. But conversely, I find that the tutors, the instructors, like this simulation. My colleagues like this simulation, use the simulation in the teaching, because they say, look at all the wonderful things I can show, look at all these really things about hearing I can demonstrate using this simulation. But the students really perhaps not interested in a lot of that stuff. And this actually possibly goes too far and tries to be too realistic. And then there's a sense then people can become a bit lost on what's going on. So curiously, this is perhaps a situation where the simpler and less sophisticated model might actually have been more beneficial as far as teaching is concerned. There's one other situation where this arose, where I built a larynx simulation. I built a two-mass model simulation, an animation of a two-mass model of the larynx. I looked at this thing after I'd built it, and it was beautiful. You could change the spring tensions and things like lengths and masses and things, and this thing vibrated and used a beautiful glottal area function and a simulated laryngograph waveform. So it was a lovely thing, and I looked at it, there's no way I'm going to be able to explain what is going on in this simulation to a student in a laboratory class. It's just way beyond. I would have to spend so much time explaining what was going on, there wouldn't be any time for them to have learned anything out of the process of doing it. It was like the gas, a bit like the gas simulation. You've got to strike a compromise between the reality and the information that you want to convey. Okay, so we've got a cochlear simulation, and one of the things that the cochlear simulation shows you is there is this kind of distinction between the processing that's to do with timbre and the processing that's to do with pitch. And one of the problems with a spectrogram is that it kind of confounds those two things. So let me just put this display, this is a spectrogram.
Mice.
This is me saying mice. And so at the top here we have a conventional spectrogram. The trouble is in this picture is that there's again lots and lots of stuff going on. So there's these black bars that are moving here. These are the movements of the articulators causing changes in the resonances of the vocal tract. And then you've got these vertical lines, these striations, which are individual glottal closures making pulses. As pulses travel up through the vocal tract and they take on the colour of the resonances as they pass through. So effectively we've got in a spectrogram a confounding of the pitch information and the timbre information. And for a lot of the processing that we're interested in doing, certainly in speech recognition, is that we want to separate out the timbre information from the pitch information. And so here's a way in which you might do that. This is a representation of the timbre independently of pitch. And here's a representation, a kind of representation of the pitch, sort of independently of timbre. So in this picture, you can see that what we've done is we've preserved the black areas where there's energy at particular frequencies, but we've lost all the fine structure in here. And I don't know why we've got all these labels on. And in this lower picture, we're trying to focus on repetition in the signal. And so this is called an autocorrelation. And so this vertical axis represents delay. And basically this says, after what delay does the signal get back in step with itself? And so you can see at this point in the word mice, there's a certain delay here, which is about sort of 10 milliseconds. So after 10 milliseconds, the signal gets back in step with itself. And obviously after 20 and after 30 and after 40, it goes back in step with itself again. Whereas at the end of the word mice, it's more like 15 milliseconds, and then at 30 and 45 and so on. So there's a longer delay before the signal gets back in step with itself. In other words, what's happened is the repetition period is increased, or the repetition frequency has gone down, or the pitch in this word has fallen, so that the striations are closer together at this point and further apart together at this point. And this is, in a way, I think of this autocorrelation picture as much more like the kind of thing that the ear is doing. It's looking at the intervals of repetition in the signal, and that's more the kind of basis of pitch information in the ear. Okay, so I don't know what we're doing for time. Okay, so we're about halfway through. So talking about timbre, then, where do these timbres come from? How does the vocal tract make these different timbres? What's the mechanism which gives us the vocal tract shapes they turn into timbres? And one way to do that is to visualize the actual articulatory system itself through an articulatory synthesizer. So take a articulatory shape and turn that into sound. So this is a little program which has an articulatory synthesizer, so it takes a shape of a mid-sagittal section, and then you can control the shape of the mid-sagittal section. So I can move the jaw up and down, I can move the tongue position forward and back, and so on, and the tongue shape, and I can open and close the lips, and so on. And at the same time, I can hear what that does. So I can make it play a sound, and then I can say, okay, well, let's open the lips. And you can, if you're really keen, you can make it say something stupid. So you can sort of move all the articulators around. And again, it's one of the things we get the students to do is to measure some vowel form and frequencies of their own speech, and then to see if they can recreate the articulatory shape here, which will give them approximately the same form and frequencies. The system actually comes in 3 different sizes, so you can have you can change it down, change the size of the pipe if you want as well, so the sound. So the same articulation, of course, ends up with a different sound depending on the size of the vocal tract. The thing, actually, one of the things you learn from trying this is it's really hard. It's really hard to go back from a sound to the articulatory shape that produces that sound. And it's kind of weird that it should be so hard. I mean, one of the reasons, of course, you've got huge amounts of dimensionality here. You've got all these sliders for moving these different bits of the shape around and moving the larynx up and down, and lip aperture and lip protrusion. So there's an awful lot of things that you could change to be able to make a particular sound. And it's not even unique. You could make a very similar sound in different ways with different settings. Which then, of course, leads to another really interesting observation. Well, if it's so hard to control a vocal tract to make a particular sound, how on earth did 9-month-old babies do it? Right? I mean, how do infants learn how to control their vocal apparatus such that they can make a sound, a particular sound, to order? So that leads to, I think this leads to another whole area that really I got very interested in, which is that what are the processes of interaction between caregivers and infants such that infants can learn how to generate sounds which ultimately can be used in an intentional way to communicate. So simply from building this animation and thinking and trying to use this animation, you then say, well, why is that hard? Why is it hard to go from sound back to articulation? And surely if it's hard, it's going to be even harder for someone with a real vocal tract, which is even more complex than this simulation. So I then said, well, okay, so we want to study the interaction between caregivers and infants so that we can look at speech acquisition. But the trouble with that is if you use real infants, is that you don't know what the infants are thinking. So the infant may think that, well, I've said an R sound, and and then the caregiver made an oo sound or something. So if we capture just the audio that infants make, or the audio that adults make, we don't know why the adult made this particular sound. We don't know why the infant made that particular sound. We don't know what the relationship is between the components. We actually have to instrument this process. We have to have inside this infant caregiver interaction, we need to know what the infant is thinking, which means we can't use a real infant, we have to use a virtual infant. So the next task was, let's take this articulatory synthesizer and put it inside a virtual infant. And then we'll get people to be caregivers for the virtual infant. The virtual infant will say things, and then the caregiver will say things back. And we'll know that the infant was thinking this, and they said that, and then they heard this, and then they interpret that as, and we can follow the chain of logic through. So the next step was to build a virtual infant. And it's called Claire, which is like KIT for language acquisition, interaction, real time, something like that. It's got nothing to do with my fact that my daughter's name is Claire. So, and she doesn't look anything like this either, fortunately. So here's Claire. I can't show you the video because when the data projector is plugged in, the video doesn't work. So just check that, turn the video on. So Claire is that vocal tract synthesizer put inside a model, a 3D model. You can see the synthesizer down here. It's put inside a 3D head, and the head sort of can look around and be vaguely animate. And Claire also processes the sound coming in from the microphone. E, oo, and so it's got a sort of primitive auditory system as well. And it can also do video capture through the webcam, so I can't demonstrate that in this setup, unfortunately. So what we can do is we can put the subject in a room with Claire, and we can be outside, and we can get Claire to do various things, and then we can video capture what these people say, and we can record how they interact with Claire. And it's really surprising how easy it is to fool people, because people will instantly lapse into infant-directed speech, even when they're presented with a flat, infant-looking head on a screen. They'll still say, "Oh, what do you think?" And raise their pitch and talk in baby language. And we have this task where we have toys on the screen, And Claire looks at a plane and says cat. And then they go, no, that's the plane, say plane. And they go, dog. And so we get this. We collect these interactions through people, and hopefully that's going to be some more ongoing work. Let me just get Claire to say something. It's a bit hard because there's not much room on the screen. But, get to that. Let's move this over here a bit. Make some Claire moving. Thank you, good. And the other thing we can do with Claire, obviously I can manipulate all the vocal tract controls as well. I can also move the head around, and I can even, with a bit of luck, I can even change the expression so I can make it sad. Oh, no, what's the matter? Happy again. Yeah, it's all right now, yeah. So it's just, you just lapse into this just automatically. It's completely stupid, really. So I mean, you've got the people. They're in a sort of soundproof chamber, and they have a screen with a computer on it, and they're talking in baby language. You're thinking, oh, this can't be real. Okay, so let's just stop that for a minute. I'm really going to leave that again in a minute. So if you're going to talk about processing sound and classifying sound and recognizing sound, you need representation. You need to choose what representations you're going to use of the audio signal for doing machine learning, or doing any kind of statistical modeling. This came up yesterday. We were talking about formants and spectral envelopes and things. So there are choices in what sound representations you want to use for doing your analysis, for doing your statistics, for doing your modeling, for doing your machine learning. And here's just a picture of some different choices.
Mice.
Here's me saying mice again. So here's a waveform at the top there. Let's do that as a spectrogram. And the spectrogram is kind of really got too much information in it. It's too rich. It's too messy. You can't really do very much with that. This is a way of getting just the spectral envelope information using what's called linear predictive coding, or LPC coding. So this is a way of calculating a smooth spectrum for, you can see it's actually in slices of length 10 milliseconds, and it generates a smooth spectral envelope for each 10 minutes. And this gives you quite a nice picture which highlights the bumps. We know the bumps are important because the bumps are the loudest bits. So the black bits, of course, are the loudest bits, hence they're perceptually most salient, and hence that's why we were interested in them. And so this particular way of modelling emphasises the detection of the bumps. And the problem with this is that typically this is done on a linear frequency scale, and we know the processing in the ear is not a linear processing scale. So just because things are so many hertz difference on this picture doesn't mean that the perceptual distance is exactly the same. So a 1,000 hertz change at 5,000 hertz might have a very small perceptual implication, whereas a 1,000 hertz change at 1,000 hertz might have a big perceptual change. So one way to sort of correct for that is to use a filter bank which has a non-linear frequency. You may just be able to see these numbers, I probably can't, but these are going up in more like a logarithmic scale here. And we've now quantized the energy in frequency bands as well as so it's horizontally and also in time vertically. And so you get kind of a cartoon picture with one energy blob per 10 milliseconds and maybe 19 blobs along the frequency axis. And so this was a very popular way of doing it about 30 or 40 years ago. Here's another representation, which is the formant representation, which says what matters about this representation is not all this beautiful grey colour. What really matters is where the dark bands are. And you can see that sometimes this works quite well. So in this I part of the word mice, it does indeed, we can indeed find where these resonances are, certainly the first two quite nicely. But the problems with format analysis is that it makes horrendous numbers of mistakes. And sometimes there are black blobs in the spectral envelope which aren't formants, and sometimes formants don't create black blobs in the spectrogram. So sometimes you have peaks which are not formants, sometimes you have formants which are not peaks. So it's a very, doing things in format analysis is very, very messy. And that's pretty much why in the machine classification and speech recognition area, formats were abandoned 30 more years ago. So what sort of representations do people use nowadays? And the interesting thing is they use the one that's at the bottom, which doesn't look like anything like any of the others at all. The one at the bottom is called Cepstral coefficients. And Cepstral coefficients are simply a way of encoding this shape. In other words, they're just coefficients which we're just saying what sort of a shape do we have? Do we have a shape that sort of goes up and then down? Or do we have a shape that goes down and then up and then down again? Or a shape that goes up and down and up and down? So it's a way of coding the shape of the envelope without really worrying too much about the fine detail. And as you move up these coefficients, the lowest coefficient here, C1, is looking at the grossest shape, and then the C2 is looking at a slightly finer detail, and 3, 4, 5, 6 are looking finer and finer details. So there comes a point in which you say, well, I've got as much information as I want, I can stop there. So typically, for no particular good reason, people tend to stop after about 12 coefficients. And what people find is generally, after that, it's the law of decreasing returns. You don't need to characterize a spectral envelope with more than about a dozen coefficients. And there's this really good reason for using Cepstral coefficients, which is that because of the way they're defined mathematically, they're pretty much orthogonal to one another. In other words, that you can, the measurement you make on one of those coefficients is independent of the measurements you make on the others. And that's not true for predictor code, it's not true for filter bank energies. The filter bank in one energy channel is very highly correlated with the energy in the adjacent channel, so that the numbers you've got are not independent of one another. Whereas in Cepstral coefficients, you've got that independence. And that means you can use the covariance matrix is diagonal, which means that there's a whole load of benefits. So you can use simple Euclidean distance metrics. You can build Gaussian mixture models with far fewer coefficients, and a whole load of benefits accrue from choosing the right representation. Okay, so let's have a look at some classification. I'm going to ask Claire to help me in this. So what I'm going to do, just if I can find Claire and fire her up again. She's still smiling, that's good. 1, 2, 3, 4. Ah, so now Claire is listening to me. And what I'm going to do is to get the sounds from the microphone to go through Claire into a sound classification system. We're simply going to kind of cluster the sounds in real time while you watch, so that you can see the kinds of sound clusters that arise simply from letting the clusters, letting the sounds come in. So let's have this working. I hope this is going to work anyway. Are you 1, 2, 3, 4, 5? So I'm speaking now, and what the system is doing is trying to put all those vectors, all those sound vectors, into clusters. It's kind of like a clustering algorithm. This particular learning algorithm is called a growing neural gas. That's kind of irrelevant. Once you get this idea that the blobs represent different kinds of clusters or different kinds of categories of sounds, and the lines sort of connect sounds which are sort of relatively similar to one another. So this display is plotting the first energy channel against the next energy channel, which is not very interesting. But if I switch this so it's plotting the first two principal components instead, we've seen that this space of possible sounds that it's picking up and building from scratch at the moment it's gradually filling out. It's deciding what particular categories of sounds it needs to explain the speech. So if I say s, we've got s over there on that side of the picture. Sh, it's over there. It's also so sh, s. Can you see the little yellow blob? Sorry, the yellow blob is the current one. Sh. I'll point. The sh is over here. S, somewhere over there. Ah is down here. E, oo, and vowels are sort of turning up over here. And in fact, if you play about it, you can usually create a vowel quadrilateral with them like E, U, E, U. Well, we're getting here. U, E, So I sort of, you see they're already getting, even after just a few minutes of speech, they're already getting distributed in the relative positions that you would expect. Right? This is just totally automatically from just looking at the sounds and seeing what kind of modeling do I need to represent the distributions of the sounds. And so you're pulling out a whole load of statistical information out of the signal completely automatically. And of course there's a lot of stuff going in the middle here just explaining silence. All the silence factors are somewhere around. So silence has to be explained as well. Okay, so let's kill that. Turn clear off. Bye-bye. Okay, so we're sort of getting closer to building a speech recognizer. Oh my God, I'm really running out of time. And one of the things that people found in building speech recognizers is that it's not just the energy at particular frequencies and times that you need, but you also need to know how these things are changing with time. And you have to have a time or a dynamic element to the spectrum. So here's me saying So here, this sound is basically with a B, a D, and a G in it. When you look at the energy contour, of course, you see these black bars representing the formants, and the vowel doesn't change, so the formant bars look horizontal. But what you're really kind of interested in is, if you're trying to identify the B and the D and the G, is really the little bits of stuff that's happening round about these edges of these transitions. And one way you can emphasize that is to essentially take the derivative of the spectrogram. So you're looking at how the energy in the spectrogram is changing with time. So this middle picture here sort of represents the rate of change of energy at each frequency. And you can kind of see that when the signal stops here, you get a white bar, which represents the energy dropping down from this middle line. And then when the energy starts up again, you get a black bar, which is where the energy is increasing. So grey is like zero, and white is a negative gradient, and black is positive gradient. You can do something even more, I think even more interesting, which I've never seen done before, and I only did this myself earlier this week, which is, well, I thought, well, that's changing things in amplitude. What about things changing in frequency? Could you track objects that are moving in frequency in the same sort of way? So you get a derivative of in terms of frequency rather than derivative in terms of amplitude. It's surprisingly hard to do. You have to look up optic flow and things like this in the video processing literature. But you can do it after a fashion, and this bottom picture is meant to represent changes in changes in frequency. It's objects which are moving in frequency. These objects needn't be peaks. These could be valleys that are moving in frequency. These are just things in the spectrum that are changing with frequency. Right? So again, this is not formant. The formants are looking at the peaks, but there's no reason why a movement of a valley couldn't be perceptually useful as well. And you hope you can kind of see that you get these movements in frequency, negative movements here going white because you're going into a B, and some positive ones coming out. And one of the interesting things, I think, is that you can start to see that the pattern of movement that you get for B is different to the movement that you get for D, is different to the movement you get from G. And this is really, going back, this is Oman and locus theory, and this is basically saying, this is really saying, there are movements in the spectrogram which are really important for perception. But rather than hypothesizing that, we're actually seeing these movements arise by finding the right representations. I'm sorry, I'm going to have to go really, really fast now. I'm about halfway through this talk at this point. Let's build a speech recognizer. What happens inside a speech recognizer? So if you go inside a speech recognizer and pull the guts out, basically what's happening, let's zoom in a bit on this. At the kind of lowest level, is it saying, let's take the speech coming in 10 millisecond chunks at a time, and then calculate the probability that this particular sound could have been produced by a particular phonological unit. That's what a recognizer does. It says, I know the kinds of kinds of sounds that are produced by different phonological units, what's the probability this particular sound was made by a particular phonological unit? So you can see that this first part of the signal here is all quiet, and you probably can't read these labels, but the label here that's most active, most black here, is the silence label. That's good. So that's good. So then we have another sort of chunk here, and there's basically only one thing that's active at this point, and that is actually the S phonetic label. So it thinks that this is the most likely thing that produced this sound is an S. So that's good, right? So that was probably a reasonable guess. And then it sees this little gap here, and it says, okay, well, I think pretty much I'm convinced it's this block here, and actually comes across as a P. Okay, so it thinks this is a P. And then it sees this next little block here, and it's a little bit confused. It thinks it's possibly a bit like an E, but it's also, I think this is a bit like an, I can't quite follow the lines across, a bit like an A, maybe. So it's a cross between an E and an A, but most dominantly an E. So.
B, B, B.
Okay, and we can move across a bit more, and there's another chunk here. And you can see that we're now starting to get some ambiguity. This chunk here, we've got sort of 3 bars that it could be. This bar represents ch, this bar represents j, and this bar represents sh. So it's not sure whether it's a ch, a j, or a sh. Okay, so so that is not bad, but it's true. And I guess you've already worked out what this is going to say. So if we play this whole thing, then we get
Speech.
To the beginning of the word speech. And what's interesting about taking the guts of a recognizer apart is that you see, although here there's less ambiguity, there are regions here which are really highly ambiguous. That it's not clear what kind of thing is going on. There are some situations where the system can make really clear decisions about what's happening. But there are other times when there's a lot of ambiguity, where this sound could have been produced by a whole range of different phonological units in different situations. So it isn't always the case that things are unique. And that means that the system cannot label the phonetic characteristics of the speech at this point. It can't make a decision at this point. It has to postpone making a decision until it can take other things into account, like what words are there in the language, what's the likelihood of one word following another word. And that's the fundamental thing that speech recognition engineers have found. That's about the only thing that speech recognition engineers have found since Bartoliniak and Mercer in 1983, which is essentially you cannot make low-level decisions. You have to postpone those decisions until you can take the broader context into account. And you can see this. You can see why this is necessary, because you still, at the lowest level, you're getting enormous ambiguity about which particular phonological units are recurring at any particular time. And you can't make that decision at this point. You have to wait and make that decision later. Are we all right just for 5 minutes?
We're going to let you go.
Okay, all right, okay, fine. I think I've only got, I've got sort of 2 more stories. Okay, so one thing I looked at a few years ago was accents, and how can you can compare one accent with another. So imagine we've got this person here.
After tea, father fed the cat.
And we've got another person here.
After tea, father fed the cat.
Well, one of the questions we want to ask is, do these people speak the same accent, regional accent in this? And one of the problems in accent studies is that you're saying, here's individual A with an accent, individual B with an accent, and you can make some measurements of individual A and individual B, and you're saying, are these measurements the same? Well, of course, they're always going to be different because you've got 2 different individuals. Right? Even if these people do have identical accents, they're still going to make different measurements for A and different measurements for B. So I've got a man and a woman. So if I measure the form and frequencies in this speaker, then they're going to be different to the form measurements I make in this speaker, because these are different people. And so a fundamental problem in accent is saying, well, how can I distinguish between those differences which are due to the individual as opposed to the differences which are due to their linguistic experience and their accent? And there's all sorts of people have tried to approach all kinds of ways of addressing this problem, either just by taking enormous studies, so you just average hundreds of people together and hope that the means are different. But of course, really you want to deal with individuals, not with groups of 100 people, because you don't know that a group of 100 people is even homogeneous to begin with. I mean, if you can't measure their accent, then you put all these people together, you just have to hope that they're homogeneous. You can't, you really want to start with just individuals and let individuals cluster into accents on the basis of whether they have the same accent or not. In other words, you let the accents arise from the data. You don't specify what the accents are in advance and hope that you're going to find them. So I proposed a different way of doing this in 2004, and this is a method called ACTIST, which is a metric for comparing accents. And the idea is basically this. You get everybody to say the same set of sentences, and unfortunately that's the key constraint. So we get this person to say, after tea, father fed the cat. And what we do is we compare their R vowel in after with their E vowel in tea, with their R vowel in father, with their E vowel in fed, and the A vowel in cat. And we look at how similar these vowels are to one another. And we just use spectral envelope metric, Euclidean distances of MFCCs. Absolutely terribly straightforward and dull. And of course what you find is you get a little map. And this map is sort of the distance between one vowel and another vowel. So you probably can't read these labels, but these labels say R in after, R in father, A in cat, E in fed, and E in tea. And so this says R in father is quite like R in after is quite like R in father. It's not so close to A in cat. It's very far away from E in head, and it's a long way away from E in E. So this is the colouring really represents the distance. The redder it is, the further the vowels are apart from one another. So let's take our second speaker. And again, we look at compare the vowels with each other within the second speaker. So we're not comparing speaker A with speaker B. We're looking at the vowels, the distances between the vowels and speaker A, and the distance between the vowels and speaker B. So we never compare formants or measurements between one person and another. We're only comparing them within the speaker. And so when we get that plot, what you see is that it's remarkably similar. In other words, the distances between the vowels for the first speaker is very similar to the distances between the vowels in the second speaker. And we can just simply compute a correlation between these two graphs. And if it's a high correlation, we say these accents are very similar. And if it's a poor correlation, we say these accents are dissimilar. Let me just show you that it works. So here's another speaker.
After tea, father fed the cat.
I hope you agree is a Birmingham speaker.
After tea, father fed the cat.
After tea, father fed the cat.
And he says after. So that's the key. But he still says father. But he says after tea, father fed the cat. And when you look at his distance table, you can see that it looks different. It looks different. That the similarities between these blobs look significantly different. If we compute the correlation between these two things, there's a much worse correlation between these two speakers. And while again, you can look up the work, but you can get surprisingly good accent identification systems using this idea. I'm getting something like, out of classifying people into 14 different regional accents, I'm getting something like 93% recognition accuracy, which is way, way beyond people can do. Mm-hmm. Something to bear in mind. Okay, lastly, this is something that's very recent, and in fact I still was programming this a few days ago. This last thing was to look at dialogue structure. Let me show you what it does first, and I'll explain what the reason for it was. So I'm going to play in some dialogue.
On the seashore is a man fishing.
Yeah.
With a yellow hat, kind of khaki-coloured top, and red trousers.
Yeah.
With a fishing rod that it goes into the sea.
Yeah, I've got a shark next to it jumping out.
Yes. Is he kind of smiling?
Well, yes. Smiling and looking menacing.
But he doesn't appear to be stuck on the line then?
No. He's
okay.
like a couple centimetres away from it.
Good.
Okay.
So what this does, basically, is take a stereo audio recording of two people speaking, and it's essentially chopping the recording up into chunks on the basis of energy, and it's colour coding it on the basis of which person is speaking at one particular time. And when two people are speaking at the same time, you get this sort of coloured bar. And once you've got this representation, you can play back.
With a yellow hat, kind of...
Yeah, I've got a shark next to it jumping out. No, he's...
And you can sort of play back bits of it and try and work out what's happening. You can play back whole turns.
Well, yes. Smiling and looking menacing.
And so the reason for this, so this is strict, really is visualization. What I'm trying to do is take a dialogue and visualize it. What does a dialogue look like? How can we turn it into a visual pattern? And how does a visual pattern, could a visual pattern be useful? And I have one application that's driven this, which is that a patient came to one of our clinics with an auditory processing deficit. They had a stroke, and it didn't really affect their production speech, but it made it very much harder for them to process speech. And unfortunately, in their job, they have to work a lot on the telephone. And he's finding it really hard to follow conversations on the telephone. Obviously, if you're face-to-face, you can ask people to slow down, repeat, and look at their lips and so on, and you can get extra help. But if someone's speaking to you on the telephone, they're much less sympathetic to the fact that you're having problems following what they're saying. So it's really important for his job that he can hold telephone conversations, but at the same time he's finding it very difficult to process. He can process speech if he's given enough time, if he can repeat things. And so the idea is, could we take this telephone conversation and then express it in a visual way? I mean, we can either do it live while the conversation is taking place, or you can use it to review a telephone conversation after the fact and you can play back parts of it. And one of the things I thought that might be useful, and we have no idea whether it's going to be useful at all, is that we could play back bits of this at different rates. So I can play back things slower than...
Yes. Is he kind of smiling?
So that's the slower speed.
Yes. Is he kind of smiling?
That's the normal speed and...
Yes. Is he kind of smiling?
Oh, you're like super speed. So again, no idea whether such a thing is going to be useful to him. But I somehow get this feeling that by taking a dialogue, which is kind of evanescent, it's gone, you can't capture it. If you can somehow hold it in your mind, then maybe that would help him process this signal. And what we're going to try and do is try this out with him and see whether that has some benefit. Well, I've gone on much too long, so I just want to finish up, come back to my original things, which was, what did Tufts say we needed to do? We needed to show the data. I think in seeing speech data, we do emphasize this problem of continuity and context dependency. It isn't until you see a spectrogram or see an X-ray of someone speaking, you realize how there's always movement, and it's always asynchronous, and there's whole lots of things going on at one time. And until you see that, you simply think that people speak as written language, and until you see that dynamics, you need that to see what's going on. I've shared with you some of the problems I've had in choosing the right level of fidelity. Sometimes I've built simulations and models which are actually too good, and they end up not having the value that I expected them to have, because the students and people simply don't see the wood for the trees. They can't see what I'm trying to say because they just get overwhelmed by the complexity of the picture. You'll notice that almost everything that I've done is real time, or it has interaction, or it has animation and movement. And I think that, again, it's really important not only to be able to see these pictures, but to say, well, what does this bit of the signal sound like, or what does this bit, or zoom in and zoom out. So interact with the visualizations as well, I think is really important. Tuft asked us to encourage comparison, and of course this does mean that we need to think carefully about what representations of the signal we're going to use. Are we going to use spectrograms which confound timbre and pitch, and or can we simplify the representations down so that we can focus on the important issues, so that we can compare one thing with another? And lastly, make large data coherent. One of the things, of course, we're very, in some ways, in speech signal, audio being a one-dimensional signal, we can always use the spatial dimension to talk about changes in time. But not only do we do that, we need to think about a way of looking at a dialogue and then zooming in and looking at, a turn, and then looking at a word, and then looking at a segment, and looking at a cycle. There should be ways in which we can use the granularity of the spatial dimension to look at the signal at different levels of quality. So I think we've done an awful lot of possibilities, and I hope that we haven't done things too wrong. We've learned a few things along the way. If you're interested in any of this stuff, as Anne said at the beginning, a lot of these programs, like the cochlear simulation and so on, can be downloaded from the departmental website. And although they're Windows software, they can be made to run on Macs and Linux systems with appropriate emulators. Thank you very much for listening.
Thank you for an absolutely fascinating presentation, Mark. Thank you very much. We should go to the break, but perhaps there's a question. People have a pressing question. If not, I do have a very quick one. Can Claire become bilingual?
Well, Claire doesn't have any language knowledge at all. Oh, no, you mean
can she be taught to be bilingual?
Well, no, I mean, the machine learning aspect of Claire is completely separate from Claire. Claire itself is just an application which provides you with the head and the articulatory synthesizer and the video capture and the microphone capture. You have to do all the hard work behind the scenes. I mean, I've been building various machine learning applications which do the interaction, which collect the data and do learning. And of course, that's where all the hard work is really. I mean, what I was trying to do was create a thing where all the horrible real-time graphics, real-time signal processing, audio capture, video capture, all that stuff you really, really don't want to deal with because it's really horrible. Put that into a package, and then behind the scenes you can write applications in Visual Basic, in MATLAB, in C or Python or whatever, and you can write applications which talk to Claire, and you can do all your machine learning stuff on another computer outside the booth, and you can do all the interesting experiments that you want to do. That's the way in which it's set up. And I'd love for people to pick it up and use it. I really wrote it for student projects, because I thought, this is the sort of thing where someone in an engineering department could say, well, I haven't got the capability within a one-year project to build one of these things, but I have got the capability to do a little machine learning experiment using this as a front end. And you can download this for free, and it just runs on a Windows computer, and then you can start to talk to it with applications that you can program yourself, and that's the motivation.
Super, absolutely splendid. Thank you. Thank you very much.